Welcome to this scientific lecture on one of the most fundamental skills in experimental science, fitting physical models to experimental data and using this process to validate hypotheses, interpret results, and discover new phenomena. The scientific method isn't just about making observations. It's about creating mathematical models that predict behavior, testing those predictions against real data, and refining our understanding when reality doesn't match our expectations. You might ask, why do we need mathematical models in science? Can't we just observe and describe? The answer is that mathematics provides a precise, quantitative language that allows us to make testable predictions. A good physical model transforms vague ideas into specific, falsifiable predictions. Without this precision, science would be mere speculation. Let me walk you through the complete process, from developing a theory to discovering its limitations. Step 1. We start with a physical hypothesis based on fundamental principles. For example, we might hypothesize that the force of air resistance on a falling object is proportional to its velocity. We write this as F drag equals B times V, where B is a constant and V is velocity. Step 2. From this hypothesis, we derive a mathematical model that predicts measurable quantities. Using Newton's second law, we can predict how velocity changes with time. For our air resistance example, we get V of t equals versus terminal times the quantity 1 minus e to the negative t over tau, where tau is the time constant. Step 3. We design experiments to measure the relevant quantities. In this case, we'd measure velocity as a function of time for falling objects of different masses and shapes. Let's consider a historical example. Galileo hypothesized that in the absence of air resistance, all objects fall at the same rate regardless of their mass. The prediction was clear. A heavy object and a light object dropped simultaneously should hit the ground at the same time. The mathematical model is h of t equals h0 minus 1/2 gt squared, where g is the acceleration due to gravity, independent of mass. Now let's dive deep into the actual process of fitting models to data. This is where theory meets reality. We collect experimental data points, each with its own measurement uncertainty. No measurement is perfect. Here we have raw experimental data points. Notice they don't fall on a perfect line. This scatter represents both random measurement errors and possibly systematic effects. The key question is, how do we find the best fit line or curve through these points? The most common method is least squares fitting. The idea is beautiful in its simplicity. We define chi squared as the sum from I equals 1 to n of the quantity yi minus f of xi all squared divided by sigma I squared. Chi squared measures the total squared deviation of our data point from the model predictions, weighted by the measurement uncertainties. We adjust the parameters in our model function f to minimize chi squared. The parameters that give the smallest chi squared are our best fit values. Let's work through a concrete example. Suppose we're testing Hooke's law for a spring. Force equals minus k times displacement. The model is F equals negative kx, where k is the spring constant we want to determine. We collect data by hanging different masses from the spring and measuring the displacement. Here's our data table with force in newtons and displacement in meters. When we plot this data and find the best fit line, we get a spring constant K of approximately 19.8 newtons per meter. But here's the critical question. How good is this fit? How confident can we be in this value? We need quantitative measures to assess whether our model is actually valid. One key metric is the reduced chi squared, written as chi squared divided by the number of degrees of freedom. Chi squared reduced equals chi squared divided by n minus p, where n is the number of data points and p is the number of parameters we're fitting. If the reduced chi squared is close to 1, we have a good fit. The model predictions match the data within the expected uncertainties. If it's much greater than 1, our model doesn't describe the data well. Either our model is wrong or we've underestimated our uncertainties. If it's much less than 1, we've likely overestimated our measurement uncertainties. Another powerful technique is residual analysis. This can reveal systematic deviations that summary statistics miss. The residual for each data point is simply the measured value minus the predicted value from our model. If the residuals show random scatter around 0 with no pattern, that's good. Our model captures the physics. But if we see a systematic pattern in the residuals, like a curve, that tells us our model is missing some physical effect. This is where discoveries begin. Let me give you a profound historical example of how residual analysis led to a major discovery, the planet Neptune. By the 1840s, astronomers had decades of observations of Uranus. But its orbit didn't match the predictions from Newton's laws of gravity when only considering the known planets. Newton's law of gravitation, F equals g times m1 meter 2 over r squared, had been incredibly successful. But something was wrong. The residuals between predicted and observed positions showed systematic deviations that grew over time. This wasn't random error. Scientists faced two possibilities. Either Newton's laws were wrong at large distances, or there was an unknown planet perturbing Uranus's orbit. John Couch Adams and Urbain Le Verrier independently used the residuals to predict where this hypothetical planet should be. They solved the inverse problem. Given the perturbations, where is the perturbing mass? When astronomers pointed their telescopes to the predicted location in 1846, they found Neptune within 1 degree of the predicted position. This was a triumph of model fitting and residual analysis. But models don't always win. Sometimes systematic deviations reveal that our theory itself is incomplete or wrong. Consider Mercury's orbit. It also showed a discrepancy. The perihelion, the point of closest approach to the Sun, precessed by 43 arcseconds per century, more than Newton's theory predicted. The excess precession was delta phi, equals 43 arcseconds per century. Astronomers searched for a planet inside Mercury's orbit, which they called Vulcan, but found nothing. This crack in Newton's theory couldn't be fixed by adding more mass. It required a completely new theory, Einstein's general relativity, which accounts for the curvature of space-time near massive objects. General relativity predicts delta phi equals 6 pi gm over c squared a times the quantity 1 minus e squared, which exactly matches the observed precession. Now let's talk about one of the most challenging aspects of experimental science: systematic uncertainties. Random errors can be reduced by taking more measurements and averaging. The uncertainty decreases with the square root of the number of measurements. But systematic errors are different. They represent a consistent bias that doesn't average out no matter how many measurements you take. For example, if your force sensor is miscalibrated and consistently reads 2% too high, averaging won't help. Every measurement will be biased. Detecting systematic errors requires varying your experimental conditions, using different instruments, or comparing different measurement techniques. Let me give you a modern example that's currently unresolved: the Hubble tension in cosmology. Scientists measured the expansion rate of the universe, called the Hubble constant, using two independent methods: observations of the early universe from the cosmic microwave background, and observations of the late universe using supernovae. Early universe measurements give H0 equals 67.4 kilometers per second per megaparsec. Late universe measurements give H0 equals 73.0 kilometers per second per megaparsec. These measurements differ by 5 sigma, meaning the probability this is due to random chance is less than 1 in a million. The question is this a systematic error in one or both methods, or is it telling us something profound about new physics beyond our current models? This is an active area of research. Let me give you practical guidelines for fitting models to your own experimental data. Guideline 1. Always plot your raw data before fitting any model. Visual inspection can reveal outliers, patterns, or unexpected behavior. Guideline 2. Start with the simplest model that could plausibly describe your data. Don't immediately jump to complex models with many parameters. Guideline 3. Always check your residuals for systematic patterns. This is how you discover if your model is missing important physics. Guideline 4. Report uncertainties with every fitted parameter. A parameter value without an uncertainty is scientifically meaningless. Guideline 5. Test the sensitivity of your fit. If small changes in your data or fitting procedure drastically change your results, your model may not be well constrained. Let's discuss how we quantify the uncertainty in our fitted parameters. The uncertainty in a parameter k is related to how chi-squared changes near its minimum. Sigma k squared equals the inverse of the second derivative of chi squared with respect to k. If chi squared has a sharp, narrow minimum, The parameter is well constrained. Small changes in the parameter value significantly worsen the fit. If chi-squared has a broad flat minimum, the parameter is poorly constrained. Many different parameter values give similarly good fits. Now I need to warn you about a serious pitfall: overfitting. With enough adjustable parameters, you can fit almost any dataset, even random noise. But that doesn't mean your model has physical meaning. For example, you could fit 10 data points with a ninth-degree polynomial perfectly. But unless you have strong physical reasons to expect such complex behavior, you're probably just fitting noise. The solution is to use physical insight to limit the number of free parameters. Each parameter should correspond to a meaningful physical quantity. Another powerful technique is cross-validation. Fit your model using part of your data, then test its predictions on the remaining data. A good model should predict well on new data. For those interested in more advanced techniques, let me briefly mention Bayesian model comparison. Suppose you have two competing models that both fit your data reasonably well. How do you decide which is better? Bayes' theorem tells us that the probability of a model given the data is proportional to the probability of the data given the model times the prior probability of the model. The beautiful thing about Bayesian inference is that it naturally penalizes overly complex models through what's called the Occam factor. Simpler models are preferred unless the complex model provides significantly better fits. Let me summarize the complete cycle of scientific discovery through model fitting. Step 1. Propose a hypothesis based on fundamental physical principles and prior knowledge. Step 2. Develop a mathematical model that makes specific, testable predictions. Step 3. Design and perform careful experiments, paying attention to both random and systematic uncertainties. Step 4. Fit your model to the data using appropriate statistical methods like least squares. Step 5. Assess the goodness of fit quantitatively using metrics like reduced chi-squared. Step 6. Carefully analyze residuals for systematic patterns that might indicate missing physics. Step 7. If discrepancies are found, either refine your model to include additional effects or recognize that you may have discovered something new. Step 8. Iterate this process until your model and data agree within the experimental uncertainties. Model fitting is both an art and a science. It requires statistical rigor, but also physical intuition and creativity. Pure statistics without physical understanding can lead you astray. You might find mathematically good fits that are physically meaningless. Physical intuition guides you toward models that make sense, that have parameters with clear physical interpretations. Remember, the goal isn't just to fit data. The goal is to understand nature, to discover the underlying principles that govern physical phenomena. Let me leave you with some final philosophical thoughts about the scientific process. Science progresses as much through its failures as its successes. When a model fails to fit data, that's not a failure of science, that's science working. Every failed model teaches us something. It constrains the space of possible theories and guides us toward better understanding. Isaac Asimov said the most exciting phrase to hear in science isn't eureka, but that's funny. When your data doesn't match your model, that's when discoveries happen. Model fitting represents the power of quantitative thinking in science. It transforms vague ideas into precise predictions that can be tested and potentially falsified. It reveals hidden phenomena through systematic deviations between theory and experiment. And it has led to some of humanity's greatest discoveries, from Neptune to general relativity to the accelerating expansion of the universe. Master the art and science of model fitting, and you master a core aspect of scientific reasoning. Thank you for your attention.